Hello everyone. Konnichiwa. I'm super happy to talk here in RubyKaigi again since 2016. I'm going to talk about the cloud native. Do you know cloud native? What is cloud native? Today, I'm going to talk how Ruby survive in the world of the cloud native. First, I'm going to introduce myself. My name is Uchio KONDO. I'm working at GMO Paperboard as a software engineer. I'm from Fukuoka now today. These are my books. Perfect Ruby and Perfect Ruby on Rails, written in Japanese. These are my OS open source products. One above is yet another OpenStack client, OpenStack client for Ruby. Below is a Haconiwa mruby on containers. My community is Fukuoka.rb meetup held in Fukuoka. And I am chief organizer of Fukuoka Regional RubyKaigi 02 held in last year. And my main weapon is 4G Splattershot Pro. Thanks, Nintendo. Let's start. At first, the title is, what is cloud native? Cloud native, as some of you know, there is an organization named Cloud Native Computing Foundation, CNCF. And CNCF promotes this cloud native movement beyond the fence of cloud vendors. There is the description of cloud native on CNCF's website. That is containerized, dynamically orchestrated, microservices oriented. These are emerging technologies. And as many of you know, containers, orchestrations, and microservices are the next key technologies for both web developers and operators. But why now? Why these technologies suddenly gathered attention at the same time? And how can we utilize Ruby across these technologies? We are Rubyists, so we'd like to continue utilizing Ruby in cloud. And to answer these questions, I need to talk about my own experience as case study. Now I'm going to talk about what I have been doing for these 3 years. It's to solve issues of Linux containers and orchestrations. Okay. The next section is how I decided to create my own container runtime. Once upon a time, I was an operator of a SaaS. My company had been running a SaaS named Scale. The service had been using containers. Even this service was released on 2012 August. 1, 2, 3, 4, 5, 6 years ago, utilizing very early version of LXC. And I got some troubles. For example, managing container config was very hard. I created containers config file with ERB via chef with parameters. And containers can't be changed on its resource allocation on the fly. And changing CPU memory on containers needs restart. And the container is too old to upgrade. Changelog between LXC 0.7 and 1.0 was too big. So I decided to create my own container runtime, aiming to make container operation easy. I learned about container internal, and which seems super interesting and cool for me. And I use mruby to implement. mruby fits this kind of system programming. And the result is the software Haconiwa. Then I ended up releasing Haconiwa and talking about it in RubyKaigi 2016 about my container. This is the logo and my video. These are Haconiwa's Ruby DSL. Small letters ですね。This is just a Ruby script, but we can customize containers such as namespace and mount point and resources. Many hooks are available in containers. This setting mount point and namespaces, and then hooks. For example, sig user one. Define sig user one hook. This is my container I created. The next session is how I released web hosting platform using my own containers with custom stack. Now that Haconiwa was released, and I could create my own containers with Ruby DSL and played with it. The Haconiwa was satisfactory to me, but my colleague NGX mruby is my colleague. Ryosuke Matsumoto, who is the author of NGX mruby, said to me that this product is so cool. And I answered thanks. And he continued, but I wonder what is the strong or distinctive point of this container, comparing with other containers like Docker or LXC. Then he said the strong point or the distinctive point is what? So I thought about it deeply, and finally I found Haconiwa's distinctive points are that two features. One is composability. Haconiwa can combine many of Linux container functionalities. This is original, such as namespace, cgroup, capabilities, seccomp, and so on. Haconiwa is also Haconiwa has also extensibility. Haconiwa has many hooks. This is more hooks than Docker or LXC. We can extend Haconiwa's lifecycle and features with programming using Ruby. So originally, Haconiwa's idea was from a web hosting service. So Haconiwa's these features are very friendly for hosting. For example, we want to control configurations, and we want to do dynamic resource management. Then my colleague proposed a new web hosting service using Haconiwa to my company. And after all, the project was started. Now, this new hosting project requires some features. One is server efficiency. Highly integrated architecture was required. This directly affects pricing. Continuous upgrade is also required. Containers should be kept being managed, such as library update and security issues, and so on. And last one is availability. So a new technology is long awaited. And finally, we found new technology. Found new technology named FastContainer. Have you heard about FastContainer? If you know about this, please raise your hand. FastContainer 知ってますか？はい。This is a little minor, but so I introduce about this. FastContainer is named after Fast CGI. This is a container lifecycle management architecture. First, container will be first up when required, for example, on the first request. And container will be running until the lifetime comes. And after the lifetime, container will be dropped, then restart once the next request comes. It's like Phoenix server pattern in VM management, but it's more agile and dynamic. Also, FastContainer requires stateless. Container states are persisted only in two places. One place is CMDB, Content Management DB, we use. Containers desired spec and states are on it. On the other word, containers are converted to CMDB's state. Another place is shared storage, such as NFS or Manager DB. These are hosting features. Users' contents are on them. And container process itself is stateless. This picture explains FastContainer. This is from container. This is a dispatcher in front of containers. When request comes, first get containers information from CMDB, and then check containers is available by this information, such as IP, port, and so on. If not available, this time invoke new container, invoking. If container is started, and the ports are listening, so the next request, dispatcher just forwards the request to container. After some time goes, system kills container after lifetime. For example, 20 minutes after. Then container is killed and returned to 1. Restart and killed. This is containers life cycle. I explain about merits for hosting of this architecture. First, resource is allocated just when required. On the other words, if there are less accesses, less resources used. Processes are continuously refreshed because lifetime is limited. This prohibits containers from getting too fat in memory. Containers have now host-server transparency. This means containers are forced to be immutable by refreshing. So they can be invoked in any host servers as the same condition. Next, I'm going to talk about implementation. We used these technologies, such as Nginx mruby and mruby CLI for system tools, and also Haconiwa. These are mruby technology. We also implement core API to control clusters. This is now written in Golang, and also scheduler for provisioning. This also written in Go, but compatible with sidekicks Redis. We create dashboard as SPA using Next.js. Sorry for not Rails. Next is sample of FastContainer. This small Ruby script is doing FastContainer. This line gets container spec via CMDB. Getting containers ID via header and getting other specs via CMDB. This example console is used. And then now we know containers IP and port, so checking IP that specific IP and ports are listening. If okay, just return this IP and port to Nginx and request will be forwarded. Then if not listening, compose the command line of Haconiwa and invoke the container, then wait until the container is ready. Please note that this code skips some of sanitization. Next slide is that a famous orchestrator Kubernetes stack and our stack. Comparing with Kubernetes stack, we use Haconiwa as runtime instead of Ranchi. Networking is used. In networking, we use simple bridge and VS, virtual ether. Orchestration is somewhat different from Kubernetes and Containerd. We create in front of Haconiwa. We create NGXML based a kind of service mesh. And also we created cluster controlling API written in Golang and named Jardin, Niwa in French, garden in French. this service mesh and this API is more interactive than Kubernetes and container do. So now we introduced new orchestration stack because we had to re-implement this layer. We wanted very dedicated, we wanted very detailed control in resource allocation and container lifecycle management. This was difficult by existing software stack at that time. We use RubyKaigi, injects mruby and Haconiwa mruby tag. This tag was very helpful to implement because it's all Ruby. And then with this architecture, a brand new hosting was released. The next section, I'm talking about how I'm creating a new orchestrator for containers using Ruby. Now that service is running, but there are a lot of tasks and issues. One of the biggest one is about container efficiency. We want to provide more user containers using less resources as possible. Imagine that 100 container in a server. Okay. This looks realizable. Next, 1,000 containers in a server. Is this realizable? We want to realize over 10,000 containers in one server. This 1,000 containers issue is very challenging. For example, the Linux kernel, the default, one bridge can have just 1,024 interfaces. This is far from 10,000. The speed is container root up speed is also a problem, especially namespace creation. The Linux namespace container requires Linux namespace, and for example, if we are using older IP root 2, IPnet NSAD is becoming slower and slower according to namespace gains. And if slab cache becomes fat, this makes unshared system code operation slow and so on. These problems about this area, my colleague Piyama writes about these system call problems, but in Japanese. So I want a sandbox for containers to solve these problems. And I want sandbox, smaller and simpler one. I want this orchestrator to use FastContainer for lifecycle management, and also require I want to just one I want just one or two VMs to set up, so it's required to less roles to deploy. And we use Haconiwa, so Haco files and root of FS are easily customizable. Then I remember that my company was using a smaller, simpler KVM management software. It's smaller than OpenStack and it's aimed to be used for development. This name is maglica. This is simplistic revert wrapper using 0MQ for RPC written in Python. By the way, creator Mizi-san was the chief architect of Scale. So I wanted maglica for containers and creating it now. Core technologies are 0MQ for simple RPC and using server engine. Do you know server engine? Oh, server engine is a concise framework for CRB to build a valid Unix demo. And it helps us to write a multi-process worker server. And I named my orchestrator marfusha. This memo is the architecture of marfusha. And I'm going to implement controller, provisioner, and subscriber. These operations are all async in 0MQ using FastContainer. But I'm sorry for it's under development. I gave priority to Splatoon. Sorry. But next section, I'm going to talk about Ruby for Cloud Native from my experiment. Now that Cloud Native seems a must, containers for application and environment portability, orchestrations are also important because all operations should be coded. Microservices as developers are organized in smaller teams like Spotify's tribes. But now looking back, CNCF, there are CNCF incubator program. In it, there is only one Ruby product, FluentD. This itself is great job. But can't we utilize more Ruby to survive in the cloud native? My answer is yes. From my experience, Ruby has its own strong points to implement it cloud native platforms. One is DSL, and another is combination of CRB and mruby. First, DSL have many merits for learning. In cloud native operations, everything is programmable. So operators should learn programming languages. Okay, but this is not always realistic because they aren't all programmers. But in my opinion, DSL is one of good solutions because Ruby's power of effectivity is also good to non-programmers to learn and use. So now I'm going to talk about YAML, static formats. Operators can use YAML. YAML is good format, but it's prone to becoming a high wall, like this curtain. And I think it's not even typed. So Ruby 3's source typing will be helpful for such type of configuration as code. Next strong point is CRuby and mruby combination. We can use both CRuby and mruby in almost one grammar. We can use CRuby in generic server, and here it is programming. And we can use mruby in systems programming. For example, if you are required to control middleware such as web servers, Redis, and so on, or even Linux itself, you can use mruby to access them easily. The strong point for system programming is in mruby is the memory management, simpler C bridging API, and its ecosystem. So, but on the other hand, what I wanted in Ruby were 2 points: better RPC solution and easier way to use many core. I want better RPC solution. RPC is required not only by microservices. It's also useful in classical multi-role architecture. Now gRPC supports Ruby, but not officially for mruby. But C or C++ is supported, so creating a binding looks good. But this spoils one of gRPC's merits. That is auto-generation of all of RPC code. And next one is using many core. Using current CRuby, the only good way is, in my opinion, workers using fork. Because going beyond GVL is so hard, and multiprocess is a classic Unix way, and it's reasonable. But in the future, Guild will be a good solution, and I'm waiting. Last section, I'm going to talk about future. Cloud native's future. One is that Kubernetes will be a de facto standard for developers and operators who want to dynamically control containers. Dynamically and directly control containers. But most of applications will be deployed to serverless platforms, especially applications that will be required to be small and agile. Now that I say Kubernetes is agnostic to containers. Do you know CRI? CRI is an interface between containers and Kubernetes core stack. Containerd and CRIO speaks CRI. Then, in the near future, Haconiwa will be run under Kubernetes. If we make an adapter that speaks CRI, And other languages can be used as Kubernetes container. And then serverless is also agnostic. A serverless provider just gives API. And the only thing developers have to learn is this API, and then they concentrate their resources to develop applications. This means for providers can choose any technologies in the back of API to solve developers' tasks and issues. Imagine cloud native for Ruby. Somebody can provide a new function as a service using Ruby and mruby, in which Ruby is fully available. Because using Ruby is reasonable to solve developers' issue. Our issue that we want to use Ruby in serverless. Isn't it? I imagine one like AWS Greengrass. This Greengrass use Node.js, both device and server. But imagine all in mruby cloud. Both device and server written in Ruby. This isn't it exciting? So I say we can create yet another cloud-native platform using Ruby and mruby. I think to be continued. This story is to be continued, but this talk is to end. Thank you. The font, I use free font. And thank you, Thinking Sans.
You mentioned about the 10K containers issue, but what is the legitimate use case of running 10,000 containers in one server? コンテナを
モアスローリーで
ごめんなさい。コンテナを1万個1つのサーバーで動かすユースケースってどういうのがあるんでしょうか？
なんですかね。ちょっと日本語コミット話なので日本語で失礼しますが、一般的なウェブホスティング、アパッチなどを使うウェブホスティングは、まあ割と当社のロリポップなどもそうなんですけど、一つのサーバーに多くて1万や2万のバーチャルホストを詰め込んでいるパターンが多くて、まあ、だからこそかなり非常に安い価格で提供できているというところがあるので、まあ、その数に近いなんかユーザーの環境を一つのサーバーで作れるか作れないかというのは非常に、まあ、今後サービスを展開する上で大事だと考えていて、まあ、そのあたりの実験を今しているという。
じゃあ10万個が同時に、ごめんなさい、1万個が同時に起動するわけではない。
1万に限りなく近い
が同時に起動する。
近く起動してもどれぐらいサービスをまともに提供できるかというところをまず知りたいということで、まずはやってみようという。
ありがとうございます。
このセッションは以上となります。ありがとうございました。
Thank you.